Scores are the results of observations of variables. So the type of observation is a measurement of a variable, and when we measure a variable through observation, we get a score. So scores result from particular measurement procedures for each variable. We use these measurement procedures consistently so we know what we're measuring, how we're measuring it, and other people can measure it in the same way and hopefully come up with consistent or comparable measurements. We would hope that all of us would be able to go out and measure the temperature and come up with accurate readings, for example. Obviously with us, it's never that easy. People are really fickle and inconsistent. Okay, so constructs and operational definitions. Constructs are things that we can't really directly observe, but they help us to describe and explain behavior. So you might come to class and say, well, I'm not motivated for class. Motivation is a construct. You can't see someone's motivation levels. In other words, it's not something that sort of flashes like a flashing light over someone's head that says this person is demotivated. Instead, you have to observe a bunch of behavior and see whether that behavior illustrates motivation or not. Now, I just said I think that our science is so fickle. So someone might look demotivated. You could see they're kind of dragging their feet coming into class. They're not smiling. They take a long time to take their notepad and pens and stuff out. And you might say, well, that's I can see through observation, through measuring their behavior, that they're not motivated. So it's operational definition is like a procedure for measuring something, like motivation, and you use the resulting measurements as a definition and measurement of the construct of the idea. Now, I said it's fickle because someone might not be demotivated. They might just be feeling sick that day or tired because of something else. They might be really motivated. They might have shown up even though they were tired because they were so motivated, but their physical behavior might show something else. But that's why our measurements aren't always valid and reliable. But the principle holds. We have an idea, general idea about something, and then we work out how to measure it, and that's the operational definition. And then after that, we can measure it, and then the measurement becomes part of the definition. So in future, we might say a demotivated student is a student who doesn't show enthusiasm for class, shows signs of physical depression during class, and so on and so forth. So in a way, these two things are interactive and rely on each other. Now, discrete and continuous variables are two different categories of variables, which are things that vary. So the levels change and can tend to be measured. Now, a discrete variable has separate or indivisible categories. You can't be in between. And no values exist between the two neighboring categories. So I'm trying to think of examples, but often these, if you are more of a constructivist, these examples don't really work that well. But you could say that someone is either, a good example would be, I guess, either native-born South African or not. Like you were either physically born in the country or not. You either have 2 children or you have 3 children. You can't have 2.4 children. I hope that makes sense. Like there are no categories in between. It's not like you go 2.1 children, 2.2 or so on until you get to 2.51 and then suddenly you've got 3 children. It doesn't work like that. I'm not trying to be silly, but that's more of a continuous variable. Continuous variable means that there's basically a continuous line, or there are almost an infinite number of levels of something. And so what we do is we ascribe boundaries and then we give labels to those boundaries. So we might use whole numbers or decimals as boundaries, explaining different levels of the variable. So there are many different values for the variable, and then we just assign values to different ranges. So those are our labels that we use to describe the level of the thing, but it's actually just indicating that it's within a certain range. So we're saying, yeah, we can actually divide this into an infinite number of parts, but that's not always that useful. So let's rather use this label, and it'll give people an idea of where we are on the scale. So discrete and continuous measurements have continuous measurements have upper and lower limits. And these are these encompass the real limits of the number. So 150 actually is the label for everything between 149.5 and 150.5. What it means is that that's just the useful label for all of those things. If you think about rounding up and down, obviously you start below the number and you go all the way to above the number. But once you get over a certain level, it becomes the next number. So it's just boundaries. And it's saying everything within these boundaries has this number. So on continuous variables, we have these real limits. They're the boundaries of the intervals for scores that are measured on a continuous number line. It's the real limit separating two adjacent scores. It's always halfway between the scores. So it is, if we're sharing space, we share it, and then halfway between us, that's where the boundary lies. So each score's got two real limits. It's got the upper limit, which is where it meets its neighbor, its lower, upper neighbor, and it's got the lower limit, which is where it meets its lower neighbor. I hope I said that the right way around. So upper limit is where you reach your neighbor that's above you, and your lower limit is where you meet your neighbor that's below you. And that limit is halfway between the two of you. Now, this is very, very important when it comes to research method. Scales of measurement. Measurement assigns individuals or events to different categories. So this is our way of creating sort of operational definitions, or being able to compare things and then describe them. And the categories can be names such as male, female, or employed or unemployed. Or they could be numerical, such as your height or your weight. Now, the set of categories, the set of possible categories I could allocate someone to within a variable, or a unit of analysis to within a variable, is the scale of measurement. So the scale of measurement is the set of categories that we can allocate a variable to, a score to, or use to allocate a score to a unit of analysis, which is one element within a sample or population. And what we do is the relationship between the categories determine the different types of scales. So to understand what scale we're using, you can look at the relationship between the categories. So in order to identify the type of scale, look at the relationship between the different categories, because these relationships do vary. And part of the reason they vary is because some of them are discrete and some of them are continuous. Like I said, you can't have 2.4 kids. That would be gross. Okay, so the different scales of measurement. These are so important if you're considering designing a research project. Pretty much because they determine firstly, certain scales are only suitable for certain things. So you have to use the right scale to measure everything. And then secondly, they're going to determine what type of descriptive and inferential stats you can use. And sometimes even whether you can test the hypotheses or not. So it's very, very important to understand these. And it's not that hard, trust me. So the first one is nominal. What I like about stats is a lot of the time the labels actually tell you everything you need to know. So a nom de plume is a pen name. And nom sounds a bit like name. And nominal is to do with just naming things or giving them a category. And there aren't any sort of measurable differences between the things in terms of quantitative differences. There's no you can't say one's higher or lower than the other one. It's just a label. So we label things and we categorize them like this, blue and green, for example. They're not quantitative distinctions, so you can't do quantitative distinctions between them. Things like gender, although that is changing a little bit, it's definitely not ordinal, but the categories are changing. Diagnosis, again, that's a bit of a messy one because sometimes we see spectrums, but diagnosis in general. A good one is whether someone's in an experimental or control group. Clearly, you can label people then. Or your arms of service, if you're in the military, your ranks, they're nominal. Not ranks, because those are actually ordinal data, and we'll get to that next. So ordinal data, again, the nice thing is the name describes it. It's to do with the order, so you rate things from highest to lowest. You can't tell how big a difference there is between each thing. You just know that there's a difference. So if you think about it, like if you run a race and I say, well, congratulations, you came first. That doesn't tell you how fast you ran or how quick you were in relation to the person who came second. It just tells you that you came first. So that's ranks, organized by size or magnitude. So where you came in class, your clothing sizes, Olympic medals. Those are things that just tell you who came first, second, and third. And they don't actually tell you how big a difference there is. We need something more sophisticated to come up with that. That's where the other two come in. Interval and ratio data. Now, interval means that there is a fixed distance or difference between each point. That's very different from ordinal or nominal data, where you can't tell the magnitude of the difference between the different classifications used or the different labels used. In this case, we can now tell how much of a difference there is, and there is a zero. So there are ordered categories, and the interval, the word interval is used here, the interval between the categories is of an equal size. So if we look at numbers, in terms of your marks in class, there's a real difference between getting 29 out of 30 and getting 30 out of 30. The difference is 1, and it's mathematically 1 question. So there is no 0 point with interval data though. So for instance, and I hope this doesn't happen, if you don't do too well in your class test, that's not to say you don't know anything about research method. All it means is that you didn't know the answers to these questions. We also use made-up 0 points, well, not made-up, but a set man-made 0 point for something like degrees Celsius. So 0 is the temperature water freezes at, and that's why it's there. And 100 is boiling point, and then they just divided it up in between so that they could get 100 grades. So 100 little tick marks. So that's a man-made 0 point. So temperature comes in here, IQ, it's definitely in here, and then golf scores above and below par. Now ratio, what I like about ratio is it's got an O at the end and it's like a 0. So ratio has a true 0. So ratio, look at the O or the 0 at the end, and you know it's the one with the true 0. So it's like interval, but with the addition of a true 0. You can have a distance of 0, what would that be, 0 millimeters or micrometers. You could have no distance. I'm not a physicist, so I'm not going to labor that example too much. But you can have zeros. The categories are still ordered, much like interval. And there's an equal interval between the categories, so you can subtract and multiply and use your maths operators. But there's this absolute 0. So although getting 0 in a test doesn't mean you know nothing about the test, about the subject, if you get 0, you definitely got 0 answers correct. So that's an absolute 0. You can get no answers correct, but that's different from not knowing anything. So it's a ratio data if we look at just the number of correct answers. The time to complete the task. Again, I don't think it'll take someone no time to complete the task, but this is 0 is the starting point. We hit the stopwatch and we start timing. And the gain and height. Gain is a ratio score because we start from 0. So gain is how much something increases, and then your starting point is 0.0. So it's got an absolute 0. So for each of these, there are different statistical tests and different ways of measuring them. So that's quite useful to know, and we will cover that. But you always have to ask yourself what type of data you're collecting, what your scale is, because that's going to determine what tests you can do. And sometimes you can be stuck with non-parametric tests if you haven't thought this through carefully enough. So where are we? We've got quite a few slides to go, it seems. So a study assesses the optimal size or number of other members for study groups. The variable size of group, is it discrete and interval? Is it continuous and ordinal? Is it discrete and ratio? Or is it continuous and interval? So what are you asking here? You're asking, are these discrete units, or are we applying labels to ranges with upper and lower limits. We're asking, does this data have a real zero? Can you have zero in this? Is it just a category? Are we ranking things? How are we calculating this? So the answer there is discrete and ratio. The question, obviously the textbook says that you can have a zero-sized group, but yes, you can, but then it's not also variable size of group. I'm being so nitpicky now, but a group is defined as 2 or more people. So, but that's just me being picky. But yeah, the answer could be discrete and ratio. They could say the optimal size of a group is 0. No, anyway. Or it's definitely discrete. You can't have half a member in a group unless they're half asleep most of the time. Now, next ones. Let's decide if the following statements are true or false. Variables that cannot be measured directly are not real. I think this is too easy for you, seriously. And the second one, research measurements are made using specific procedures defined ahead of time. Well, for the first one, constructs can only be observed indirectly, but are the subject of much research. So we look at behavior that indicates what's going on between people's ears. It's sort of the basis of behavioral sciences, is we look at what's observed and we work backwards from there. And then operational definitions are sure, consistent measurements and service definitions of constructs. So we always decide those in advance. Otherwise, it's just exploratory, really ambiguous research. So this is another bit that's quite important in this slide series. Statistical notation. We use operations and notation, okay, when we calculate inferential and descriptive stats, okay. Appendix A in the textbook has a mathematical review, but stats also uses some specific notation, okay. So we use maths notation, and then we also use stuff that's specific to us. The scores are referred to as X and Y. So X is the independent variable and Y is the dependent variable. N is the number of scores in a population, and then that's capital N. Small n is the number of scores in a sample. Remember, population, parameter, sample statistic. Okay, so the first important one is summation notation, and this is something you might not have seen before. Many statistical procedures sum a set of scores, so they add them up, they add them all together. And that the summation sign, this, would you call it, it looks a bit like an E, I guess, or it stands for summation. And the sign is followed by a symbol or equation that defines what is summed. So it's an instruction to add something up. So I've put a resource up, I hope, but I will upload a resource on BODMAS, and you must understand the basics of BODMAS. But summation happens after operations in brackets. So remember, that starts with brackets. And then remember, BODMAS goes on to orders. So if you've got any squaring or anything like that, then that happens. Then you've got multiplication or division, and then summation happens. So summation happens after all your brackets, after squaring and all that stuff, all your orders, after multiplication and division, but before other addition or subtraction, and you work from left to right, all of these things. Okay, so sum of x squared plus 47 instructs you to square each score and add 47 to it, then sum the numbers, square each score, add up the squared scores, then add 47 to that sum, add 47 to each score, square the result, and sum those numbers, add up the scores, sum that sum, and then add 47. So let's go back to BODMAS, and let's go back to the slide before. So the slide says that summation is done after operations in parentheses. We don't have anything in brackets. After squaring and multiplication or division, we have a square. And summation is done before other addition or subtraction. So sum of x squared plus 47 is instructing you to, firstly, square all the scores. Okay, so the squaring happens first. Then the summation happens, and then you add 47. And this is like learning to drive a car. There are rules. We use the rules. and we use them consistently so that everyone can use the same language. Okay. So, which of the following equations is true or false? Now, the equal is making the statement that whatever the value would be on the left, if you substituted out x, whatever or all the x's in this case, whatever the value on the left is would be the same as whatever the value is on the right. Okay, so the first one is sum of x squared equals sum of x squared. Okay, are those things the same? Now we've got to evaluate that. Sum of x squared. If we think about it, we are supposed to do brackets first. There are no brackets. Then we're supposed to do orders, so things like squaring. And then we're supposed to do summation, and then we're supposed to do addition and subtraction. So we see that there's a square there. So what this is actually saying is that we must square all the x's and then add them together. On the other side, it's in brackets sum of x squared. And because there are brackets, it's saying, listen, whatever's happening in the brackets must happen first. So that means we must add all the x's together, and then we must square them. Square the result. So are those the same thing? We'll see on the next slide. Wow. So much trepidation. What could come next? And under that, we've got two brackets. So it's saying add x together, add all the x's together, and then multiply them by the sum of all the x's together again. And then they're asking, is that equal to adding all the x's together and then multiplying that by the sum of all the x's together? I think you can see where this is going. So the top one is not correct. They are not the same thing. Okay? The second one is just the same formula written out in two different ways. And that's the end of our slides for this week. Thank you so much. And now I have forgotten how to stop this blinking thing.